Good day, everyone. So now let us discuss transformers. So we will focus on the section 2.5 of the electric machinery fundamentals of Chapman. So according to section 2.5, it is the equivalent circuit of the transformers. Okay, so as per definition based on the book, a transformer is a device that changes AC electrical power at one voltage level to AC electric power at another voltage level through the action of magnetic field. So the basis of the transformer operation, we can refer to the four basic principles of the magnetic field. For the basis of transformer action, it is a time-changing magnetic field induces a voltage in a coil of wire if it passes through that coil. So it is clearly stated that when a time-changing magnetic field passes through a coil, it induces a voltage that will be utilized by the transformer to either step up or step down. So let me share screen to you my PowerPoint. Okay, so as you can see, there are several kinds of transformer. There are small transformers, there are mounted transformers, there are three single phase transformer banks. Okay, so okay, for the discussion outline, in this discussion, we will tackle the losses present in a transformer and also the main point, the equivalent circuit of a practical transformer. Okay, so let us first discuss the losses present in a transformer. Okay, so as you can see, there are four losses that are evident in the transformer. So first is the copper loss. So copper loss are the resistive heating losses in the primary and secondary windings of the transformer. They are proportional to the square of the current in the windings. Next is the eddy current losses. Also, they are resistive heating, but now it is in the core. As compared to copper loss, resistive heating is in the windings or in the coils. Meanwhile, for the eddy current losses, it is in the core. Also, the hysteresis losses. So hysteresis losses are associated with the rearrangement of the magnetic domains in the core. Okay, so if we happen to observe, eddy currents and hysteresis losses are in the core. So therefore, they are otherwise called as core losses. Next is the leakage flux losses. So these fluxes which escape the core and pass through one of the transformer windings. Okay, so when they pass, they escape, they produce a self-inductance in the primary and secondary coils, and the effects of this inductance must be accounted for. Okay, so these are the fluxes that didn't make it to the destination. Okay, for example, if the flux is coming from the primary winding, along the way they escape and they didn't reach the secondary winding. So that is the leakage flux. It is best understood if you take an analogy. Okay, for example, if you shovel sand, so along the way there are sand particles that will fall, that will not reach the destination. Okay, so the primary winding is the point where you shovel the sand, and the secondary winding is the destination or the final or the goal, yes, destination of the said flux. Okay, let's now go to the equivalent circuit. Okay, so first, when we consider the equivalent circuit, there are some important considerations that need to be made. Okay, for example, first thing is the self-inductances. So where does this came from? Okay, as mentioned earlier, self-inductances came from the leakage flux. Now, these fluxes that escaped and made its own inductances. Okay, therefore, it is called self-inductances. Okay, these self-inductances are modeled in the equivalent circuit as, since it is an inductance, so therefore it is modeled as inductor. Okay, so for the next, the magnetization current. So it is proportional to the applied voltage and is lagging by 90 degrees. Okay, so the magnetization current IM, voltage applied, and is lagging by 90 degrees. It can be modeled by a reactance XM, X sub M, connected across the primary voltage source. Next is the core loss current. So if we happen to remember, core loss current is composed of two losses. Okay, so what are these? They are eddy current losses and the hysteresis losses. So as compared to magnetization current, the applied voltage is lagging by 90 degrees. This current is now in phase with the applied voltage source. Okay, so it is quite noting that if we remember magnetization current, it is lagging by 90 degrees. However, for the core loss current, it is in phase, meaning they are the same. They are in rhythm with each other. Okay, next is, here is an example of an equivalent circuit modeled with an ideal transformer. Okay, so the last part we will try to solve one example regarding equivalent circuit. Okay, so these are the two considerations that need to be made. Okay, so when we try to draw an equivalent circuit, we must therefore note where it is referred. Okay, so for example, in the left side of the screen, the equivalent circuit is referred to the primary voltage level. Okay, in the right side of the screen, it is referred to the secondary voltage level. Okay, also, in an equivalent circuit, there are impedances present. No, so impedances, a complex resistance. Okay, it is composed of a resistance and a reactance. So therefore, if combined, they are impedance. Okay, so for the primary impedance, we will not get the primary and the secondary resistances itself, but we will try to model them as equivalent resistance in the primary and the equivalent reactance in the primary. Also, the equivalent resistance for the secondary and the equivalent reactance for the secondary. So when we try to get the equivalent resistance and reactances of the circuit, we must know the turns ratio. We must know the turns ratio of the said circuit. So the most common thing is based on their voltage levels. So let us now go to the example. So I have prepared an example for you guys. Okay, so it said here that a 20 kilovolt ampere 8000 over 480 volts distribution transformer has the following resistances. Okay, so for RP, a resistance in the primary, there is 32 ohms. For the reactance in the primary, 45 ohms. The resistance in the secondary, 0.05 ohms. The reactance in the secondary, it is 0.06 ohms. And the resistance in the core, 250 kilo ohms. And the reactance in the magnetization, it is 30 kilo ohms. Okay, we are tasked to find the equivalent circuit of this transformer as referred to the high voltage side. Okay, so let us remember that we are referring it to the high voltage side, which is the primary side of the transformer. Since 8000 is in the primary side, so therefore it is the high voltage side. Okay, first things first, we must first consider the turns ratio of the circuit. Okay, so A is equal to 8000 over 480. We can get 16.67. So this value is very important in determining the equivalent circuit of the transformer. Okay, so given the formula, okay, so we must get now the secondary impedances as referred to the primary side. So we will only focus on the secondary impedances since we are going to refer it to the primary side, which is the high voltage side. Okay, now for the resistance of the secondary voltage as referred to the primary side. Okay, so we can see that there is a prime, RS prime here. So it signifies that we are referring the secondary resistance to the primary or the high voltage side. Okay, so now using the turns ratio, we can get, we will square the turns ratio. We will square the turns ratio, multiply it by the secondary resistance itself, which is 0.05. It is equal to 13.9 ohms. Okay, so we now have the secondary resistance as referred to the primary side or the high voltage side. So now we will go to the reactance. Now again, secondary reactance, we will get the secondary reactance, which is to be referred to the primary side. Okay, so we have here reactance 0.06, 0.06 ohms. So same thing, we will square the turns ratio multiplied by the reactance of the reactance of the secondary coil. So we can get 16.7 ohms. Okay. Now we have our secondary resistance and reactance as referred to the primary side. So the main task of this example is to draw the equivalent circuit. Okay. So now we will try to draw the equivalent circuit. We will always remember that it is referred to the high voltage side. Okay. So it is modeled just like this. Resistance series connected with the inductance, the primary inductance. Next is in the core, the impedance of the core. Same thing, resistance and reactance, but in parallel. Lastly, the equivalence. So the values that we acquired a while ago. So it is like this. Okay, this is connected. This is connected. So this, since we are in the primary side, so this is the primary side, no, coined as VP, which is 800. Next is secondary side, which is 480. Okay, so in the secondary voltage or in secondary side, we can get it by multiplying the turns ratio. Okay, so here you must be familiar that this is the primary side. This is the impedance of the core, and these are the values that we've got now a while ago. Okay, so the primary resistance is equivalent to the reactance is J45 ohms. Next, let's go first to the core, 250 250 kilo ohms. Okay, for the impedance, for the reactance, we have 30 kilo ohms. Okay, so for the values that we've acquired a while ago, we have the secondary coil, secondary impedance as referred to the primary coil. Okay, next is the reactance. So J 0.7. Okay, so let us indicate the current present. So I, since we are in the secondary side, I2 over the turns ratio. Here, this is IP. I guess we need to add the polarities. Okay, polarities, positive and negative. So I guess go back to the problem. So we are tasked to find the equivalent circuit of the transformer as referred to the high voltage side. Okay. So after getting the secondary coil as referred to the primary side, secondary resistance and the secondary reactance as referred to the primary side, we now have the equivalent circuit of the transformer here. So I hope you have understand something. This ends our lecture here. Thank you and good day. Stay safe, stay at home.